Stop scrolling for a second if you're watching the sky this week. Hit subscribe, because 3i Atlas is sliding into a setup we almost never get to watch in real time. And if it does anything weird near the sun, we'll see it fast. A lot of space stories are loud but empty. This one is quiet but dangerous because it's built on timing. 3i Atlas is an interstellar visitor, and it's moving toward its closest swing by the sun, the moment when sunlight, gravity, and speed squeeze everything into a short window. If it's a normal, natural object, that window tells us what it's made of. If it's not normal, that same window is the best place for it to change the game. Now, before anybody runs off yelling aliens, let's set one rule that keeps us honest. Big claim, boring proof. If somebody says contact, the proof has to be so dull it hurts. That means we start with what real science can test. Trajectory, light, gas, dust, heat. And the way gravity shapes motion, whether the object wants it or not. So what exactly is happening here? 3, I-Atlas is approaching perihelion, which is just a fancy word for closest point to the Sunday. And when an object does that, it's like running past a bonfire at full speed. Even if you don't touch the fire, you feel it. The surface heats. Ice can turn straight into gas. Dust gets dragged out. Jets can form. And those jets can act like tiny thrusters, pushing the object just enough to change its path a little. That right there is normal comet behavior. That's the boring version. But now we bring in the part people keep focusing on. Could it use the sun like a slingshot on purpose? There's a real physics trick called an Oberth effect. Here's the street version of it. If you hit the gas when you're already moving very fast, the same push gives you a bigger boost than if you hit the gas while you're moving slow. Near the sun, an object is moving fastest. So any extra push right there, even a small one, can change the next leg of the trip in a bigger way. That's why perihelion is not just a photo moment, it's a decision point. Now, for a normal comet, there is no decision. It just reacts. Heat in, gas out, tiny push, and we measure it. But if you want to imagine the spicier possibility, some kind of technology, you don't have to invent magic. You just need control. If something can time its outgassing or release material in a controlled way, it could steer slightly without looking like a rocket. In theory, not proven, just physics. So we have 3 buckets of outcomes, and none of them require fantasy. 1, it does nothing unusual. It follows the predicted path, maybe with small natural jet nudges. 2, it shows a big unexpected change in trajectory. That would be rare, and it would instantly trigger serious attention. 3, it shows tiny changes that look too clean or too timed to be random. That's the hardest one, because nature can fake clean sometimes, and humans love patterns. Now, the title you're working with is about alignment. People hear alignment and think of astrology or doom. That's not what we mean. Alignment here means geometry, a temporary lineup of big masses like Jupiter, Earth, and the inner planets, where their positions create a very specific 3D stage. It's like a camera rig in space. When bodies line up in certain ways, they change what we can see, when we can see it, and how gravity might shape a path. And the reason Jupiter matters is simple. Jupiter is the boss of the solar system, outside the Sunday. It's the big bouncer. It can bend trajectories. It can capture objects into temporary or even longer orbits. And it can also fling things out with huge speed. So when an interstellar object heads toward a region where Jupiter has strong influence, you don't treat it like a casual flyby. You treat it like a billiard table with a giant bumper. Now here's where I slow the pacing and keep it real. A lot of online simulations look impressive, but they're not all equal. Some are just pretty. The real high accuracy tracking is done using careful observations and orbital solutions. NASA Jet Propulsion Laboratory is one of the main places people trust for precise orbit updates, and they work with observation networks to keep objects tracked. The way they do it is boring and beautiful. Repeated measurements, error bars, and constant updates as new data comes in. So when you hear it's lined up perfectly, your first question should be, according to who? And how tight is the uncertainty? Because space is huge, and close can mean millions of kilometers. Now, let's talk about what we can actually learn during this perihelion window. Light is a fingerprint. When sunlight hits dust and gas, it scatters, it absorbs, it glows at certain colors. And if you have the right instruments, you can tell what chemicals are present. That's why big observatories matter here. Hubble has a long history of spectroscopy records that can help compare how comets and strange bodies behave in light. The James Webb Space Telescope is even stronger for certain infrared signatures, the kind that can reveal ices, organics, and heat patterns. On the ground, places like Keck Observatory in Hawaii can do extremely sharp observations when geometry allows. And across the world, major facilities tied to the European Southern Observatory contribute to tracking and follow-up on objects that matter. So if 3I Atlas is just a weird comet, perihelion is where it confesses its chemistry. You might see water signatures, carbon dioxide, carbon monoxide, dust composition, the kind of stuff comet scientists at places like the Harvard-Smithsonian Center for Astrophysics talk about when they compare active comets. And if it's unusually dry or unusually rich in certain gases, that becomes a story, a real story, not a tabloid one. Now, about the WOW signal and Sagittarius and the center of the Milky Way. That region of the sky is special in a simple way. It's dense, it's bright in radio, it's busy. The WOW signal came from a direction in Sagittarius, which is also the general direction where the Milky Way's center lies in our sky. That doesn't mean it's connected to 3I Atlas. It means humans love connecting dots when the dots are in the same part of the sky. But it's still useful to mention for one reason. It reminds you how hard radio astronomy is. Space is noisy. Arecibo legacy data, even though that telescope is gone, is part of the long story here. Years of radio observations taught scientists what real signals look like and how easily noise and one-off events can trick us. And people like Ronald Bracewell at Stanford talked about ideas like messenger probes and ways a civilization might leave signals behind, not as proof, but as thought experiments to guide searches. So if you're going to mention the alien probe idea, you do it like this. You present it as a concept, then immediately bring the viewer back to what would count as evidence. Because if we ever see a genuine artificial signature, it would show up as something that doesn't behave like nature across multiple measurements. Not a single odd moment, not a vibe, not a rumor. Now, the alignment part. Let's paint this in a way that a kid can understand without killing the awe. Picture the solar system as a skating rink. Planets are skaters moving in lanes. Most of the time, a random visitor comes in from above the rink at some weird angle, cuts across, and leaves. Interstellar objects should be like that. Random angles, random timing. But if the visitor comes in close to the same flat lane where planets skate, it feels less random. Not impossible, just less likely. That's what people mean when they say, why is it so close to the ecliptic plane, the main plane where planets orbit? Again, not proof of anything, just an eyebrow raise. And if, during early January 2026, several planets appear in a rough line from our point of view, that's more like a camera setup than a cosmic ritual. It could affect observing windows, it could affect how bright certain things look, it could affect how the story feels, but gravity doesn't care about your calendar. So here's the real question you want viewers to carry. What changes after perihelion? Because before perihelion, the object is inbound, heating up. After perihelion, it's outbound, cooling down and revealing what survived the heat. If it's fragile, it may break apart. If it's icy, it may shed a lot of material. If it has odd stability, that becomes interesting. Now let's talk about toward Earth fear, without being fake. People hear trajectory change and think impact. Most trajectory changes are tiny and harmless, and even a sizable change still has to line up with Earth's position at the same time in 3D. Earth is not a target sitting still. It's moving fast, and it's small compared to space. So the honest way to frame it is this. The main risk is not it hits us tomorrow. The main risk is we don't fully understand it, and we're watching how it behaves under extreme conditions. That keeps tension without lying. Now, you also mentioned Jupiter as a possible destination. That's actually a smart focus, because Jupiter is where weird things can happen without Earth being in danger. An object passing near Jupiter's sphere of influence can get captured temporarily or redirected. A tiny push at the right moment can change a flyby into a loop. That's just orbital mechanics. And if 3I Atlas passes through a region where gravitational forces are strong and complex, it becomes a natural lab for testing whether its motion is purely passive or influenced by outgassing. This is where NASA-style reporting gets fun, because it's a real detective story. You don't need to invent a monster. The math is the monster. The math is what corners the truth. Now let's drop in another credible anchor that tells viewers we're not guessing. Voyager 1 telemetry data is still a symbol of what long missions teach us about space environments, communication limits, and how small forces can add up over time. Voyager teaches a simple lesson. Out there, tiny effects matter. A slight push, a slight drift, a slight timing change, and decades later, you're somewhere else. So when we talk about a tiny perihelion maneuver, we're not talking about a movie engine flare. We're talking about small forces with big consequences over distance. Now, I want to do something important for watch time. I'm going to give your audience a simple checklist. 3 things to watch that makes them feel smart, not scared. 1, brightness behavior. If it brightens in a way that matches normal comet dust production, fine. If it shows sharp, unnatural changes that don't match distance and phase angle trends, that's worth attention. 2, outgassing signatures. If instruments detect common comet gases in expected ratios, fine. If it's unusually low in water but high in other volatiles or shows strange temperature patterns, that's worth attention. 3, trajectory residuals. This is the boring gold. If tracking shows the object deviates from gravity-only predictions, scientists model non-gravitational forces. If those forces fit a normal comet jet model, fine. If they don't, that's where serious papers start. Notice what's not on the list. A vibe, a headline, a random screenshot. Now, because you want this to feel like a live report, we keep the tone urgent but controlled. Here's how you say it. Right now, 3I Atlas is approaching the one point in its entire pass where the solar system forces are strongest. Heat is highest, speed is highest, and gravity is setting the tightest curve. If it behaves, we learn what it is. If it doesn't behave, we learn what it is even faster. And that's why people are watching. Now, one more piece from your summary, the Carrington event comparison. The Carrington event in 1859 was a massive solar storm that messed with telegraph systems. People like to bring it up because it's a reminder that the sun can punch civilization in the mouth when we're not ready. And it's true that space weather can line up with certain cycles and conditions. But here's the careful truth. Planetary alignments do not cause solar storms in any simple, proven way. The sun does what it does mainly because of magnetic cycles. If someone claims a straight cause, you push back, so you can say this instead. Sometimes, interesting solar events happen around times when people are paying attention to the sky. That doesn't mean the alignment caused it. It means the sky was being watched, and history got remembered. That's honest and still spooky. Now, let's tighten the mystery again. Why does this alignment idea feel so intense to people? Because it feels like a stage. It feels like the solar system is lined up like an audience, and 3I Atlas is stepping into the spotlight near the Sunday. And humans are not great at watching spotlights without imagining a performer, so we stay grounded. The performer is physics. The spotlight is perihelion. And the unprecedented part is not magic. It's that we might get a rare chance to observe an interstellar object with modern instruments across a key window and compare it to what we learned from past odd visitors. Now imagine this with me, because this is where the viewer leans in. In the days around perihelion, observatories are racing the clock. Data's coming in. People at research centers are checking light curves. Some teams are running models late at night. Amateur astronomers are trying to spot it through the glow. And in the background, the orbit solutions get updated like a heartbeat. Tiny changes, new numbers, new uncertainties shrinking. It's not dramatic like a movie. It's dramatic like a courtroom. Every new measurement is a witness. And the verdict isn't alien or not. The verdict is, what does the evidence allow? So let's keep the one open question that matters the most. If 3I Atlas does change course, is it a messy, natural change or a clean, timed change? Because messy is nature, clean is rare, and rare is where the story lives. So here's where it gets real. Because the closer 3I Atlas gets the sun, the less room it has to hide behind maybe. Distance is a great mask. When something is far away, you can blame almost anything on bad angles, weak light, or noisy data. But near perihelion, the sun turns into a harsh interrogation lamp. The heat rises fast. The glare is intense. The speed spikes. And if the object has any weak spots, this is where they show up. Think about it like this. A normal comet coming in from deep cold is basically an icy dirt ball that's been asleep for ages. It wakes up when sunlight hits it. First, you get faint activity, then stronger jets, then a growing cloud of gas and dust around it. That cloud is called a coma, and it's basically the object sweating into space. And the key detail is this: comets are messy. Their outgassing is uneven. Their jets switch on and off. The surface cracks. Dust comes off in weird patterns. You get chaos that still follows physics. So if 3I Atlas behaves like a normal comet, it should look messy in a natural way. But if it behaves too neatly, too rhythmically, too timed, that's when scientists start leaning forward in their chairs. Not to shout aliens, to ask what model fits. Now, people always ask the same question at this point. How do we even know if it changed course? Because to a normal person, space looks like a flat map. You see a dot in the sky, it moves, and it's easy to think it's headed right at us. But in real tracking, the story is all numbers. Observatories measure the object's position against background stars over many nights. Those measurements feed orbit calculations. NASA Jet Propulsion Laboratory is one of the places known for publishing precise trajectories and uncertainties. And they don't do drama. They do error bars. They do confidence regions. They do updates. So a real course change is not one video clip. It's a pattern in the residuals. Residuals are just a simple idea. You predict where the object should be if gravity is the only force. Then you compare that to where it actually is. The difference is the residual. If residuals stay small and random, fine. If residuals start trending in one direction, then you ask what force is pushing it. For comets, that force is usually outgassing. And if you're wondering how strong a comet jet can be, it doesn't have to be strong like a rocket. It just has to push a little, consistently, over time. Like blowing on a paper boat. One breath won't move it much. But keep blowing, and you'll see it drift. Now, there's another layer that people miss. Near the sun, we can learn chemistry faster. If you're observing with instruments like the James Webb Space Telescope, you can look for infrared fingerprints that tell you what ices and organics are present. That's not a guess. Molecules absorb light in specific ways. Water has a signature. Carbon dioxide has a signature. Carbon monoxide has a signature. Methanol, ammonia, lots of stuff has signatures. And on the optical side, Hubble spectroscopy history is useful for comparing odd behavior to known comets. Ground-based giants like Keck Observatory can also do high-quality spectra when timing and sky position allow. And it's not just the big telescopes. There's a whole global chain of smaller observatories that do follow-up work. Professional and skilled amateur teams can capture light curves, brightness changes over time, that help confirm whether the object's rotation is stable or tumbling. Rotation matters more than people think. Because jets come from specific surface regions, if the object is rotating, the jet should sweep around. That can create periodic patterns in brightness. That's normal. But if the jet keeps pointing the same way, even when rotation should move it, that becomes odd. Now, let's ground this again, because I'm not trying to turn your video into a conspiracy buffet. There are 3 boring reasons an object can look guided when it's not. 1, our viewing angle changes quickly near perihelion, so geometry can fake a clean pattern. 2, outgassing can self-stabilize in weird ways, especially if the nucleus shape channels gas like a nozzle. 3, Dust can create optical illusions. A thin dust sheet can look like a straight beam. Nature can cosplay as technology without trying. So the job is not to decide the story early. The job is to watch what survives multiple checks. This is also where the alignment hype can trick people. When planets line up from our viewpoint, it feels like everything is connected, but most of that is line of sight. It's a camera trick. The solar system is three-dimensional, and the objects are still separated by huge distances. However, alignments do matter in one important way. Observing windows. Sometimes the sun's glare makes it hard to track something. Sometimes an object is in the daytime sky. Sometimes it's too close to the horizon. Sometimes it's behind the sun from Earth's point of view. Sometimes Jupiter or other planets are in a better position to help us measure the object's path by gravitational influence. So if the early January 2026 lineup changes, who can see 3i Atlas and when, that can affect how quickly we get good data. Now, you mentioned the origin direction, Sagittarius, and the Milky Way center. Here's a clean way to present that without making it silly. Sagittarius is a busy part of the sky. The Milky Way center is in that direction. There's a lot of stars, a lot of dust, a lot of radio noise. Historically, it's also the area tied to the WOW signal. That doesn't mean 3i Atlas is connected. It means our minds are wired to connect intense things to the same place. But it also reminds us of a real scientific point. Signals are hard. If 3i Atlas is doing anything that creates radio emissions, it would have to stand out against a loud background. And that's why SETI-style work is careful, slow, and often frustrating. Concepts like Ronald Bracewell's old idea of messenger probes are interesting, but they're not evidence. Evidence is repeatability. Evidence is something you can predict and test. Now, we pivot to the sun itself, because perihelion is not just about the object. It's also about the environment. The sun is not just a lamp. It's a storm engine, solar wind, magnetic fields, energetic particles. All of that becomes more intense closer in. And when an object passes through that region, it can interact with the solar wind in ways that shape its tail and its plasma environment. If you want to make this feel like a NASA report, this is where you bring in the solar missions that literally watch the sun for a living. Parker Solar Probe has been diving closer to the sun than any spacecraft before, tasting the solar corona environment. ESA and NASA's solar orbiter also watches the sun and measures the solar wind and magnetic fields. SOHO has a long legacy of monitoring solar activity and seeing comets graze past the sunday. Stereo has helped us see solar eruptions in 3D. Why do these matter to your story? Because if the solar wind is especially active around perihelion, it can change how the tail looks, how dust spreads, and how the object's environment behaves. So if viewers see a tail do something weird, you can keep them calm by saying, yeah, solar wind can do that. It can fold tails, it can blow them sideways, it can create sharp structures. You keep the mystery, but you don't let it run wild. Now, let's talk about the scary possibility that doesn't need aliens. Fragmentation. When a comet-like object gets heated hard, it can crack. Pieces can break off. Sometimes you get a chain of fragments. Sometimes you get a sudden brightness spike because fresh ice is exposed and starts outgassing. That would be a huge moment. Not because it's a threat, but because it tells us what the object is made of. Fragile means comet-like. Strangely stable under heat means unusual structure. And if you want to build tension without lying, you focus on this line. The sun is the stress test. Now, another thing that makes people uneasy is the idea of a clean maneuver. So let's define what that would look like in a way the viewer can picture. If a natural object is pushed by jets, the push direction is tied to the sun's heating. It tends to align with the day side. It tends to vary as the object rotates. So the push is usually noisy. A controlled maneuver, if it existed, could show up as a thrust-like effect that starts and stops at very specific points, or aims in a direction that doesn't match the sun-facing geometry, or remains stable in a way that doesn't track rotation. But even then, you still have to eliminate a ton of natural explanations, because some comets do produce jets from strange areas. Heat can travel under the surface. Gas can vent from cracks that stay active longer than expected. So the honest tone is, if the data looks clean, it's interesting. If the data looks clean across many instruments and many nights, it's serious. Now, viewers love a countdown, but we don't want fake countdowns. So we do a countdown without numbers. We describe the approach in phases, like a news report. At first, the object is still inbound, faint, building. Then, the brightening rate increases. That's the moment observers start comparing notes. Then, the object enters the danger zone of observation, near the sun's glare, and tracking gets harder. This is where bad information spikes online, because people fill the gap with imagination. Then, perihelion happens, and the object is at maximum stress. Then, it comes out the other side, and we see what survived. That's the story arc. Now, you also mentioned Jupiter as a major player, possibly Earth, and also the idea of capturing or redirecting. So here's a clean, dramatic way to say it. After perihelion, the solar system stops being a straight road and becomes a room full of doors. Some doors lead out. Some lead into deeper encounters. Jupiter is one of those doors. If 3I Atlas passes through a region of strong gravitational influence, small changes matter more. That's why tracking after perihelion is just as important as tracking before, because a small deviation early becomes a large positional difference later. Now, I want to keep your viewers engaged with something they can do, something that makes them feel involved, not with dangerous advice, with observation literacy. So you can say, when you see a headline that says, "It changed course," ask these 3 things. Was that change measured by multiple observatories, or is it one person's simulation? Is the reported change larger than the known uncertainty, or within the noise? Did a credible tracking group update the orbit solution, or is it just a dramatic graphic? That turns your audience into smart viewers, and they'll stick with you longer, because you're not treating them like kids. Now, let's bring the alignment back in, but make it feel like a hook. Because the word alignment by itself is vague, so you paint it like this. Early January 2026 is a moment when the inner planets are arranged in a way that makes the solar system feel like it's facing one direction, like a camera pan. Earth, Jupiter, and the inner worlds create a geometry that is unusual enough to make skywatchers pay attention. And while that doesn't cause anything, it does shape something important. It shapes when we can see. It shapes what parts of the sky are crowded. It shapes the background noise. And it shapes how fast rumor spreads compared to real data. That's a modern reality. Space events are now social events. Now, I want to dial the tone closer to your earlier line. The one you used that was perfect. If the claim is huge, the proof has to be boring. So here's the boring proof we actually want next. We want consistent astrometric tracking as the object passes through perihelion. We want spectroscopy that identifies what it's outgassing, if anything. We want a light curve that shows its rotation behavior. We want modeling of non-gravitational forces. And we want those models to either fit comet physics or fail clearly. That's it. If those boxes get checked, we get a real story. And here's the emotional punchline of this whole thing, without any fantasy. This is one of the only times in your life you might watch a visitor from another star system pass through our neighborhood, get cooked by our sun, and leave again. That's wild on its own. And if it does anything we don't expect, it won't be because the universe wanted to scare us. It'll be because our understanding is still small. So we watch, quietly, carefully. And we don't let the internet decide the verdict before the data even walks into the room. Because right now, the most honest sentence we can say about 3I Atlas is this: we don't know what it will do at perihelion, but whatever it does, the sky will record it. And the people with the right instruments will notice. And when that happens, the next update won't be vibes. It'll be numbers. It'll be light. It'll be motion. And that's when we'll know whether this was just a strange natural visitor or the strangest test our solar system has hosted in a long time. And here's the part nobody likes, but it's the part that decides everything. Perihelion is not just hot, it's also messy for observers. Because the closer an object is to the sun in the sky, the harder it is to see. The sun's glare can wash out faint details. The object can end up in daylight for some locations. And sometimes the best observing window is short, like trying to read a street sign while driving past it at full speed. So this is where the story becomes a race between two things: how fast 3-eye atlas changes, and how fast humans can measure it cleanly. That's why this is not just one telescope doing a heroic zoom in. It's a whole relay team. Space telescopes, ground telescopes, small survey cameras, radio observers, people calculating orbits, people checking the same numbers twice because one mistake becomes a rumor in 5 minutes. This is also where you hear the words people hate, but you need them. Uncertainty. That word sounds like we don't know anything, but it doesn't mean that. It means science is being honest about the size of its error bars. And with an interstellar object, your sample size is tiny. We've had only a couple true interstellar visitors confirmed. That means our normal is not very well trained. It's like judging all music after hearing 2 songs. So, yes, weird is possible, but weird does not automatically mean artificial. Now, because you want this to feel like a real investigation, here's the next step. You split the whole situation into 2 questions. Question 1, what is it made of? Question 2, what is it doing? And those 2 questions talk to each other. If it's mostly ice and dust, it should show classic comet chemistry when heated, and its doing should match outgassing physics. If it's mostly rock, you'd expect less dramatic outgassing, and its doing should look more like a passive flyby, with tiny changes mostly from gravity. If it has unusual chemistry, that changes how it reacts to heating. Some materials vent differently. Some form insulating crusts. Some trap gases and then release them suddenly. So when you hear someone say, it's acting like a rocket, you don't argue. You ask a better question. Do we see the chemistry that would naturally cause that push? Because that's the boring proof again. Now let's talk about the thing people keep missing when they talk about alignment. Alignment is not a magic spell. It's a geometry that changes what close means. For example, if 3-eye atlas passes through a part of space that is near Jupiter's influence, you can get outcomes that look dramatic without any engine. A tiny change in speed near a big planet can bend a path a lot. It can also change how long the object hangs around a region. It can even create a temporary capture into a looping path. That has happened to other objects in different ways. So there's a danger here, and it's not danger from the object. The danger is misreading gravity as intention. Gravity can make a path look like a purposeful turn, especially when Jupiter is involved. That's why, if you want to keep your viewers smart and still hooked, you keep repeating one clean line. A turn by itself proves nothing. The reason for the turn is the story, and the reason is found in the data. Now, how do we separate gravity from outgassing? Tracking, this is where those boring people win. The orbit nerds. The ones who don't sleep much when something interesting is in the sky. They take measurements over time. They compare them against a gravity-only model. If the object is deviating, they add non-gravitational forces, usually a comet-style jet model. If that fits, you've got a natural explanation. If it doesn't fit, it doesn't mean aliens. It means the model is missing something. Maybe the object's shape causes unusual jet behavior. Maybe its rotation is complex. Maybe there's a delayed outgassing response, like heat soaking through layers and venting later. Comets can be weird like that. There's also a classic trick comets pull that feels spooky. They vent when you think they shouldn't. You'd expect venting to be strongest on the day side, where the sun is hitting. But heat doesn't only live on the surface. It can travel under a crust. Gas can build up and escape later, even when the surface is rotating into night. So if you see jets from a night side, you don't panic. You look for thermal lag models. Scientists at places like the Harvard-Smithsonian Center for Astrophysics talk about this stuff all the time when they compare different comet behaviors. Now, here's another big reason people get spooked. The word interstellar, it sounds like a monster movie. But interstellar just means it came from outside our solar system. It could be completely normal for its home system. It only looks strange to us because our solar system has trained our expectations. Imagine someone brings you a fruit you've never seen before. You might call it unnatural, but it's just unfamiliar. That's interstellar objects in a sentence. Now, you also mentioned the Milky Way center, Sagittarius, and the WOW signal area. Let's treat that respectfully without turning it into a conspiracy scrapbook. Radio astronomy has a long history of strange signals that ended up being human-made interference or natural space phenomena we didn't understand at first. The WOW signal is famous because it was strong and weird and it didn't repeat in the same way. But here's the rule. If something is truly intelligent communication, it should be repeatable or structured in a way that stands out against nature. A one-time blip is interesting, but it's not a handshake. So when viewers hear Sagittarius, you can say, yes, that direction is special because the sky is busy there. It's a crowded neighborhood, lots of stars, lots of dust, lots of radio noise. That means our brains can connect unrelated things just because they share a direction. Now, do we have tools to listen? Yes, but listening is hard. The Arecibo legacy matters because it helped build the mental library of what real cosmic signals look like and how often weird is just noise wearing a costume. And ideas like Ronald Bracewell's messenger probe concept are useful because they help scientists ask better questions, like what would a probe do if it wanted to be found? But again, none of that is proof about 3I Atlas. It's context. It's the vocabulary of the search. Now, we bring it back to the sun because the sun is the judge during perihelion. There's one more solar piece that makes early January feel tense: solar activity. We're in a modern world where space weather can hurt tech. Power grids, satellites, GPS, radio communication, aviation routes. So when you mention the Carrington event, you do it carefully. You don't say alignment caused it. You say it reminds us that the sun can surprise us. And we're now more vulnerable than people were in 1859 because our daily life is wired into electronics. That's a real fear, and it's grounded. Now, let me give your viewers a simple image they can hold on to, because this keeps watch time. Picture the sun like a giant river of invisible wind. 3I Atlas is a leaf moving through that wind. As it passes closest, the wind is faster and rougher. If the leaf is shedding dust, the wind will shape that dust into tails, sheets, and beams. Some of those shapes will look clean. Some will look like lasers. And that's where the internet will lose its mind. But science will do something boring and powerful. It will compare the shape to the solar wind conditions. This is where missions like Parker's Solar Probe and Solar Orbiter matter, because they measure the solar wind and magnetic environment closer to the sun than we used to. SOHO has a long record of watching objects near the sun too. So if you see a tail do something sharp, you can say, solar wind can do that, magnetic fields can do that, light scattering can do that, and if it still looks weird after those explanations, then it stays on the board as unexplained, not alien. Now, here's a part that makes your audience lean in, because it feels like detective work they can understand. A real technological object would need a reason to change course. So ask, what target makes sense? Earth is the emotional target, but it's also the hardest and least likely target because Earth is small and moving, and a collision would destroy the probe and waste the whole mission if the probe had a mission. Jupiter is a smarter target for a probe if you wanted to hide, observe, or use resources. Jupiter's magnetosphere is huge. It's noisy. It's chaotic. It could be a good place to mask signals. Mars is also a human obsession target. But again, that's us writing the story. The honest approach is this: don't guess the target. Watch the geometry. Watch the path. Now, you also talked about a rare lineup in early January 2026. Here's how to make that feel big without lying. There are times when the solar system's layout gives you a rare chance to compare measurements from multiple angles, like different cameras around a stage. Earth is one camera. Space telescopes are other cameras. And when planets sit in certain parts of the sky, you get better reference points, better timing, better conditions for follow-up. So the alignment is not a doom event. It's a measurement event. And measurement events are where mysteries die, or where they become real. Now, I want to keep the pacing hooking. So let's add a second open loop that's simple. After perihelion, the object has to show its after photo. If it's natural, it will likely have a predictable pattern. Activity rises near the sun, then fades as it moves away. Dust production changes, brightness drops. If it's unusually stable, or if activity begins after perihelion in a strange timed way, that becomes interesting. So the after photo is a big part of the story. You don't need to scream during perihelion. You can let the after photo do the talking. Now, one more credible anchor, because you asked for authoritative names that flow naturally. Voyager 1 telemetry data is a reminder of how we handle long-distance truth. Voyager sends tiny signals across huge distances, and we interpret them carefully. We don't trust one glitch. We look for patterns. We cross-check. That's the same mindset we need here. One clip is not data. One odd chart is not proof. Patterns across independent teams are where reality shows up. Now, let's talk about the one thing I actually want your viewers to feel. Not fear of aliens. Fear of being overconfident. Because the real scary thing in space stories is not that the universe is full of monsters. It's that we confuse our guesses for facts, so we keep it human. We admit what we don't know. We watch what we can measure. And we don't let the excitement turn into nonsense. Because 3I Atlas is already a miracle. Even if it's just a dirty snowball from another star. It crossed interstellar space. It wandered into our sun's grip. It's giving us a free science experiment. And now it's stepping into the hottest, fastest, most revealing part of its entire visit. So the next question is not, is it alien? The next question is way more practical. When it hits perihelion, does it behave like a messy natural object? Or does it behave like something that knows the timing? And if it knows the timing, we don't jump to a conclusion. We tighten the checks. We ask the boring questions. And we watch the numbers like they're a heartbeat. Because in space, the truth doesn't shout. The truth repeats. The truth survives cross-checks. And the truth, sooner or later, shows up in the orbit. There's a moment in every good mystery where the suspect walks past a security camera. Not because they're guilty, just because the lighting is finally good enough to stop guessing. That's perihelion for 3I Atlas. It's the point where sunlight hits hard, speeds are crazy, and any active behavior has to show up in the physics, not just in vibes. So here's the question that quietly controls the whole story. What kind of push can nature create? And what kind of push would make scientists frown? Because if you're hoping for a Hollywood engine flare, forget it. Space doesn't do loud, space does subtle. A comet's push comes from gas escaping the surface. That gas carries momentum. It's tiny, but it's real. The tricky part is the push depends on the object's shape, spin, and how the sun heats it. Two comets can have the same size, and one looks calm while the other acts like it's got a grudge. So if we see a change in motion, the first boring explanation is still the strongest. Non-gravitational acceleration from outgassing. NASA Jet Propulsion Laboratory lives in that world. They've modeled this for comets for decades because that tiny extra push is exactly the thing that makes orbits drift over time. It's why predictions tighten as more observations come in. Now here's where it gets spicy without being silly. If 3I Atlas vents gas in a way that's rhythmic, timed, and unusually stable, it could look like microthrusters, even if it's natural. A crack can act like a nozzle. A trench can channel gas. A crust can open like a valve. Nature can fake engine behavior just by having the right shape and the wrong day. So how do you keep your story intense without turning it into nonsense? You look for consistency across instruments because one telescope can be fooled by geometry. 10 telescopes in different places using different sensors are much harder to fool. That's why you'll hear the same list of names showing up when something matters. James Webb Space Telescope for infrared chemistry and heat patterns. Hubble for visible and ultraviolet spectroscopy, history, and comparisons. Keck Observatory for sharp, ground-based spectra when it's visible. ESO facilities for follow-up, especially when objects are low in the sky for one hemisphere and better for the other. And soon enough, The Vera-Rubin Observatory will change the whole game for finding and tracking fast movers, because it's built for wide field survey speed. This is what makes this moment feel different from old sky mysteries. The toolbox is better now. Now, let's talk about the alignment idea in the title, but in a way that ordinary people can picture. Imagine the solar system as a dance floor. Planets aren't lined up like a straight ruler. They're spaced around the sun, like dancers moving in circles. Sometimes, from our viewpoint, they appear to cluster on one side. That's the alignment people talk about. It doesn't summon anything, but it can create a weird situation where several big gravity wells are positioned in a way that makes the same patch of space feel like it's under a spotlight. And when you add 3I Atlas threading through that general neighborhood, the human brain does what it always does. It assumes the timing means intent, but timing can be coincidence. The real reason this matters is simpler. Alignment changes what we can observe and when. It changes who gets the best view. It changes which instruments can track cleanly. It changes how easily people can make convincing looking graphics that are totally wrong. So the galactic alignment isn't the threat. The threat is misinformation during a short, high-stakes observation window. Now, you brought up Jupiter, and I'm glad you did, because Jupiter is the part of this story that stays thrilling without putting Earth in the headline for no reason. Jupiter has a huge gravitational reach. It also has a gigantic magnetosphere, basically a bubble of magnetic chaos that can trap particles and create radio noise. If 3I Atlas passes into a region where Jupiter's influence matters, the path can bend in ways that look dramatic even when it's purely gravity. Also, Jupiter has something called a Hill sphere, which is just a fancy way of saying this is the region where Jupiter starts winning the tug of war against the Sun for nearby objects. If the object goes near that region, then tiny changes in speed or direction can decide whether it simply swings by or whether it gets tugged into a different lane. That's not aliens. That's celestial billiards. Now, you also mentioned the Oberth maneuver idea. Let's keep it simple. If you want maximum change from a small push, you do it when you're moving fastest. Near the sun, the object is moving fastest. So, if it can create any push at perihelion, whether by natural jets or something more controlled, the effect on its long-term path could be noticeably larger than the same push far from the sunday. That's why perihelion is the decision point in the story. Not because we're waiting for a movie twist, because the math is most sensitive there. Now let's get to the part that turns your audience into detectives. Because when viewers feel smart, they stay. Here are the 3 tells that would matter most after perihelion. And they're all boring on purpose. First, does the orbit update cleanly? If tracking groups keep adjusting the orbit and those updates converge smoothly, that suggests the object is behaving within expected physics, even if it's unusual. If updates keep swinging wildly, that usually means we're missing observations, or the object is venting unpredictably, or the measurements are hard because of glare. Second, do the chemical signatures make sense? If James Webb or ground-based spectra show common comet gases and common dust that supports natural behavior, even if the object is from somewhere else. If it's unusually low in water but rich in other volatiles, that's still not proof of technology. It's proof the object had a different history. Third, does the activity match rotation? If the brightness pulses match a rotation period and the jets sweep as expected, that's normal. If jets appear to stay aimed in a strangely stable direction that doesn't fit the spin behavior, then scientists start arguing not about aliens, but about shape models and thermal lag and vent geometry. And thermal lag is a big one. People think heat is instant. It's not. Heat can soak under the surface, build pressure, and vent later. That can make gas appear from regions that are technically in night at that moment. It feels wrong. But it can be physics. So if you want fear in a NASA style, the fear is not aliens are coming. The fear is we don't yet know which natural explanation fits best. Because that's honest uncertainty. And uncertainty makes humans itch. Now, let's deal with Sagittarius and the wow signal angle, because you can use it for mood without becoming irresponsible. Sagittarius is where the Milky Way looks thick. It's crowded, bright, noisy. The wow signal came from that broad direction in the sky, which also points roughly toward the Milky Way's center. That's why it's so tempting to tie everything to that direction. It feels like the universe is pointing somewhere. But here's the sober truth. A crowded sky produces more weird coincidences. If you want to bring up the old search ideas, you can mention Stanford's Ronald Bracewell concept of messenger probes as a thought experiment that shaped how scientists think about possible technosignatures. You can mention how Arecibo legacy data helped build the culture of skepticism in radio astronomy. Because one suspicious signal can ruin your week, and 5 suspicious signals can ruin your career if you get excited too early. That's part of the charm of real science. It doesn't let you win easily. Now, let me pull one more thread that keeps your audience locked in. What if 3i Atlas does nothing weird at all? Would the story die? No, because even a perfectly natural interstellar object is still a rare gift. It's material from another star system, stress tested by our sun, observed by our best instruments, and compared against a sample size that's still painfully small. That's like finding a message in a bottle, even if the message just says ocean. And if you want to keep the pacing sharp, you frame it like a countdown without using cheap timers. Inbound, it's building tension. Near the sun, it's under stress. Outbound, it reveals the aftermath. And the aftermath is where you'll see the truth most clearly. Did it brighten and fade like a normal active object? Did it fragment and shed pieces? Did it stay oddly stable? Did its tail behave like solar wind physics, which missions like Parker's Solar Probe and Solar Orbiter help us understand better than we used to? Did the orbit settle into a predictable path, the way JPL-style orbit solutions tend to do when an object is behaving? Or did it keep producing residuals that don't fit any clean model? Again, not aliens, just a problem. And problems are what science runs on. Now, there's one more reason your early January 2026 window feels intense, and it has nothing to do with 3i Atlas itself. It's us. Humans are going to treat that window like a live event. People will clip videos, post graphs, slap big words on small changes, and the loudest voices will try to win the story before the data is even finished arriving. So your job as the calm NASA-style narrator is to do something powerful and rare online. You slow the viewer down. You tell them what counts. You tell them what doesn't. And you keep one question hanging in the air, the one that pays off later. When 3i Atlas comes out from perihelion and heads toward the Jupiter neighborhood, is its motion explainable with messy natural forces? Or does it look strangely timed? Because if it's messy, it's probably nature. If it's strangely timed, the investigation gets serious, not louder. Serious means more telescopes, more papers, more modeling, more arguments between very smart people who hate being wrong. And that's the good stuff. Because in real space stories, the scariest moment isn't a jump scare. It's the moment the boring explanations start running out. And we're not there yet, not even close. But we are approaching the one part of the journey where the universe stops letting the object stay mysterious by distance. The sun is about to do the interrogation, and the answers, whatever they are, will show up in the only language space can't fake for long: light, chemistry, and motion. There's a weird psychological thing that happens when an object survives perihelion. People expect a big reveal right at the closest point to the sun, like the universe is going to pull off a mask in front of everyone. But a lot of the time, the real reveal happens after. Because on the way in, you're guessing what the object will do under stress. On the way out, you're reading the damage report. And damage reports are honest. If 3i Atlas is fragile, it should come out looking changed. Maybe brighter at first because fresh ice got exposed, then fading as the easy stuff boils away. Maybe it sheds dust in a new pattern. Maybe the tail becomes messy. Maybe the light curve changes because pieces broke off and the spin changed. If it's tougher than expected, that's also a reveal. It means its inside structure can take heat and stress better than a typical loose snowball comet. That's one of the cleanest, most real mysteries in this whole story. Not is it alien, but why is it built like that? And when I say built, I mean by nature. Nature can build things that feel engineered just by throwing pressure and time at them for millions of years. Now, Here's where the story shifts from pretty sky to serious tracking. Because after perihelion, the big question becomes the orbit, not the pictures, the orbit. If you want to hold your viewers, tell them this simple truth. A camera can lie. An orbit is harder to lie with. Because the orbit is not one photo. The orbit is dozens of nights of measurements, checked against models, checked again, and then updated. And when tracking teams update orbits, they aren't doing it to entertain anyone. They're doing it because tiny differences matter later. This is where people hear a phrase and they panic. Close approach. So let's diffuse that in a way that still keeps tension. Space is huge. Close can still mean millions of kilometers. But close can also mean close enough for gravity to matter. And Jupiter is the king of that kind of close. Jupiter is the big bouncer in our solar system. It's the body that throws comets around, traps some, ejects others, and changes the paths of visitors who would otherwise just pass through quietly. So if 3I Atlas moves into a region where Jupiter can tug it, this isn't just a cool view moment. It's a math moment. This is when small effects get amplified. And that's why the Jupiter phase is the part you build suspense around, because it's grounded. Now, there's another layer that makes Jupiter feel like a stage. Jupiter's environment is noisy. Its magnetic bubble is huge. It crackles with particles. It generates radio emissions that scientists have studied for decades. A spacecraft like Juno has been living in that chaos, mapping Jupiter's gravity field, magnetic field, and deep structure. So here's a real thought that can keep the audience leaning in without you promising anything crazy. If a strange object wanted to hide, Jupiter would be a loud place to do it. That does not mean it will. It just means the environment is complicated enough that unusual signals could be masked, and also complicated enough that natural effects could look strange. It's the perfect place for confusion. And confusion is where myths grow. Now, let's bring this back to the biggest risk in this story. And I'm not talking about impact. I'm talking about misinterpretation. Because once the internet decides something is controlled, every normal behavior becomes proof. A slight curve becomes steering. A sudden brightness change becomes an engine burst. A sharp tail becomes a laser. This is why your story needs a spine. A set of rules you keep repeating so the viewer trusts you. Rule 1, one data set is not enough. Rule 2, repeatability beats shock. Rule 3, if the proof is exciting, it's probably not proof. Now, since you want this to feel like a NASA report, but still cinematic, you can paint a scene that's real. Imagine Earth at night, and somewhere in a control room, people are staring at numbers that update quietly. No dramatic music in the room, just someone saying, run it again. Someone else saying, compare against last solution. Someone else saying, check the calibration. Because the boring steps are the steps that protect you from getting fooled. Now, your audience needs a hook to stay through the boring steps. So give them a simple contest. If 3I Atlas is natural, the models will catch up to it. If it's doing something truly unexpected, the models will keep chasing it and failing to explain the same pattern. That's the tug of war. Nature versus our models. Now, let's talk about the chemistry again, because this is where the object can feel creepy without any fantasy. When an interstellar object heats up, it can release stuff we don't see often in local comets. Not because it's artificial, because it formed in a different fridge, different star system, different mix of gases, different radiation history, different impacts, different time. So if it comes out with unusual ratios or strange dominance of certain molecules, that's a big deal scientifically. And this is where James Webb becomes important in a way viewers can understand. Webb doesn't just take pretty pictures. It reads the object's breath, what it's releasing, what it's made of on the surface, what kind of dust is in the coma. And because it's infrared, it can see heat signatures and certain chemical features that are hard to get from the ground. Now, you can keep the tone tense by saying this. The object doesn't need to send a message to change human history. It only needs to be chemically unfamiliar enough that it forces scientists to rewrite what they thought interstellar visitors should look like. That's already a shakeup. Now, let's bring in one more big instrument idea that feels like a plot twist, but is just science: polarization. Light has a direction, like it prefers to wiggle in certain ways. Dust and surfaces can polarize light differently depending on shape and texture. If an object shows extreme polarization, that can mean unusual surface grains, unusual roughness, or unusual dust geometry. This is one of those subtle measurements that can make an object feel wrong without any fake drama. And it's also the kind of thing professionals look at when they're trying to decide if the dust is typical comet dust or something stranger. So your viewer hears, "It looks too clean." You answer with, "Let's check polarization." They hear, "It's blue." You answer with, "Blue can come from dust and scattering, but we should compare spectra and polarization together." Now, there's one more open loop you should plant here, because it pays off later and it doesn't require you to lie. The night side jet problem. People will keep repeating it because it sounds like a cheat code, so you keep it simple. Heat can lag. Gas can vent from beneath. Rotation can make jets look like they're coming from impossible places when they're actually coming from cracks that were heated earlier. So if a jet appears on the wrong side, you don't label it artificial. You label it needs thermal modeling. And that phrase alone makes it feel serious. Now, about the galactic alignment phrase. If you want it to feel scary in a grounded way, here's the angle that works. The alignment is less about space magic and more about timing pressure. When several interesting sky factors stack up at once, the science community gets less sleep, the public gets more anxious, and misinformation spikes. So the unprecedented part is partly human. The stress of a big event in a short window. That's a real modern phenomenon. Now, I want you to picture what happens next after perihelion, because it's quiet, but it's the hinge. The object comes out. Observers start catching it again as it moves away from the sun's glare. Measurements improve. Orbit solutions tighten. And then one of three storylines becomes obvious. Storyline 1. It behaves like a strange but natural interstellar comet. The push is explained by outgassing, the chemistry is odd but believable, and the orbit settles. Storyline 2. It behaves like a natural object with rare geometry. It stays weird in appearance, but the motion fits physics once we model it better. Storyline 3. The motion stays stubbornly off model, even after we throw every normal explanation at it. And if storyline 3 happens, the correct reaction is not screaming, it's escalation of scrutiny. More telescopes, more teams, more independent checks, more papers, more arguments. Because when the claim is huge, the proof has to be boring. And the boring proof takes time. Now, I'm going to keep one question hanging because this is what keeps watch time. When 3I Atlas comes out from perihelion and heads toward the Jupiter neighborhood, do we see the kind of messy, uneven push that comets do? Or do we see a push that looks too neat? And if it's neat, the next question is even sharper. Is it neat because it's controlled? Or neat because we've finally seen what a truly different kind of natural object looks like? Because that's the thing people forget. Space is not obligated to match our examples. We only think normal exists because we've mostly studied our own backyard. This is an outsider, and outsiders don't follow local habits. The first real punch in the stomach happens after perihelion, not during it. During perihelion, 3I Atlas is half rumor, half glare. It's too close to the sun from our view, and the best instruments are doing their work quietly, like locksmiths in the dark. But once it starts sliding back out into darker sky, that's when the universe stops letting us hide behind maybe. And on that first clean night back, the measurements land like cold water. Not a dramatic photo, not a glowing engine, just positions, tiny dots on star maps, numbers with decimals. And those decimals decide the story. At NASA Jet Propulsion Laboratory, the orbit solution tightens. The model is rerun, gravity only first, then gravity plus a standard comet-style push. Then a push with different jet angles, because the tail geometry matters. Then the same process again, because one team's answer isn't enough. Independent checks are the whole point. That's how you keep your name out of tomorrow's apology post. Meanwhile, the chemistry side of the room is looking at something else entirely. Infrared fingerprints from the James Webb Space Telescope start to settle into a pattern. Not a message, not a signal, a pattern of gases and dust that either behaves like a natural object under heat or doesn't. Webb is basically reading the object's breath after it ran past a furnace. And that's where the tension sharpens. Because two things can be true at once. The chemistry can look natural while the motion looks weird. Or the motion can look natural while the chemistry looks strange. Either way, something is going to make scientists uncomfortable. Because uncomfortable means we don't have enough examples yet. The public wants a single headline, but the data is doing what data always does. It refuses to fit in one sentence. Now, the key moment hits like this. The orbit fits, but only if you accept a very specific kind of push. Not just outgassing, a push that is timed. Not perfectly timed like a machine, but timed enough to make the models narrow down to a few explanations instead of 50. And suddenly, the story stops being about what people think they saw in a tail photo. It becomes about whether the same kind of push repeats again and again in the same phase of rotation, under the same solar conditions, in a way that makes sense for a cracked, spinning body. Because if it repeats, you're not dealing with one weird night. You're dealing with a behavior. This is where you bring your viewers close and keep them calm. You remind them that comets can absolutely do this. A crack can behave like a nozzle. A trench can channel gas like a pipe. A crust can seal and then pop like a soda bottle that got shaken for 10 years. Thermal lag can heat the inside, and the wrong side can vent later because the heat arrived late. That's not sci-fi. That's basic physics with a strange object. Astronomers like Karen Meech have spent years explaining how small bodies can fool our expectations, especially when you only see them for a short time. And at the Harvard-Smithsonian Center for Astrophysics, researchers have argued for years about how easily we overread intention into motion when we don't fully understand the object's shape, spin state, and material. So the responsible move is simple. You do not call it contact. You call it a test. Can nature make this behavior without breaking the laws we already trust? Now, the next part of the climax arrives with Jupiter looming in the background like a giant silent judge. Because the moment 3I Atlas starts moving into a region where Jupiter's gravity begins to matter, the whole problem becomes more sensitive. Small changes get magnified. A tiny push at the wrong time becomes a noticeable bend later. That's why this phase matters so much. Not because Jupiter is a stage for aliens, but because Jupiter is where math becomes unforgiving. And for a few days, it genuinely feels like the solar system is holding its breath. Juno's long work around Jupiter becomes relevant in a weird way. Not because Juno is watching 3I Atlas, but because it reminds us how intense Jupiter's environment is. Charged particles, magnetic turbulence, radio noise. A place where signals and dust and plasma can behave in ways that confuse even experienced teams. So the question sharpens again. Is the strange behavior still there when Jupiter starts pulling? Or does it fade into the expected mess of comet physics? That's the moment your viewers want. The clean fork in the road, and the fork arrives quietly, like all real science does. It shows up in residuals. Residuals are just the difference between where the object should be if your model is right and where it actually is. If the residuals shrink and behave, the model is winning. If the residuals stay stubborn, the object is teaching you something. So the teams do the boring things again. They check for processing artifacts. They recheck calibration. They compare different telescope pipelines. They cross-check using different observatories, because one instrument can fool you, but 5 instruments in different places are much harder to trick. Keck in Hawaii weighs in with precise spectra when the geometry allows it. ESO facilities add follow-up from the other side of the world. Hubble's long history of spectroscopy becomes a reference point. Even if it isn't staring at this exact object at this exact minute, because the library of how comets normally behave matters when you're judging something that refuses to act normal. Then, space weather enters the room like a rude neighbor. Solar wind conditions shift. Parker's solar probe and solar orbiter data gives context for what the sun was doing, because tails and plasma interactions can sharpen, twist, or straighten depending on the solar wind and magnetic field. That matters because some impossible tail behavior is just the sun drawing with invisible ink. And now we hit the hardest, most honest line in the entire story. Even if 3I Atlas looks unnatural to us, that does not mean it is artificial. It can be natural and still be outside our comfort zone. It can be a traveler from a system that makes comets with different ratios, different dust, different organics, different crusts, different trapped gases. The universe has had a lot more time to experiment than we have had time to observe. So here's what the climax becomes in a NASA-style story that doesn't lie. It becomes the moment the best boring explanations either hold or they don't. If they hold, the fear shifts into awe, because then you're watching a real interstellar object behave naturally in a way we've rarely measured before, and the implication is huge without any aliens at all. It means our comet models were local. It means the universe makes more varieties than we've named. It means interstellar comet isn't one category, it's a whole zoo. If they don't hold, the fear shifts into discipline. Not screaming, discipline. More telescopes, more papers, more independent teams, more caution with words. Because if something is truly unexplained, the quickest way to kill truth is to hype it too early. And this is where you land the key emotional beat. You tell the viewer something that feels almost unfair. The universe does not owe us easy answers, but it does reward patience. That's the real tension, not the monster behind the door, the silence after the knock. So as 3I Atlas keeps moving, the solar system stops feeling like a backdrop and starts feeling like a machine you can hear working. The sun heats. The object vents or doesn't. The orbit bends, Jupiter tugs. The data repeats or it doesn't. And the whole internet can scream whatever it wants, but the orbit will not care. The orbit will tell the truth slowly. In the end, the clearest conclusion you can give your audience is also the most powerful. Whatever 3I Atlas is, it has already exposed how small our sample size is. We built normal out of a handful of comets and asteroids from one solar system. Then a visitor arrived from somewhere else and reminded us we might be judging a whole universe using local habits. NASA and university teams will keep doing what they always do when something refuses to behave. They'll keep measuring it until the mystery shrinks. And if the mystery doesn't shrink, they'll build new models until it does. That's how this always ends, not with a single headline. With a new chapter in what humans can explain. And if you're the kind of person who likes the scary part of this story, here it is, plain and simple. The scary part isn't that something is coming. The scary part is that our best tools are finally good enough to notice when something doesn't fit. And we're still learning how to stay honest when that happens. So keep your eyes on the boring things. The orbit updates from NASA JPL, the chemistry fingerprints from Webb, the follow-up spectra from places like Keck and ESO, the solar wind context from Parker, Solar Probe, and Solar Orbiter, and the long, patient habit that made Voyager missions legendary in the first place. The habit of trusting patterns over panic. If you want the next video, it's on your screen right now. And it goes deeper into what Jupiter can do to an interstellar visitor when the timing is just right.